My name is A.L. Goldman. I teach physics at El Camino College.
Let's say I have a spring of spring constant K. One end of the spring is attached to the fixed wall. I then introduce an x-axis which points in the direction of extension of the spring. I set the origin of my x-axis at the resting position of the moving end of the spring. Then I attach a mass m to the moving end of the spring and pull on the mass until the mass is located at x equals a. At this moment, the mass is at rest, v equals 0, but then I'm going to release the mass, and the mass will then oscillate back and forth between x equals plus a, x equals minus a, x equals plus a, x equals minus a, and so forth. We have seen in an earlier video that the maximum speed of the mass occurs when the mass passes through x equals 0 in either direction. That maximum speed is equal to the amplitude of the motion a multiplied by the square root of the spring constant divided by the mass. Now we're going to look at a different problem. Again, I have a spring of spring constant k, and again I will attach one end of the spring to the wall. Again, I'm going to have an x-axis in the direction of the extension of the spring, and I'm going to put the origin of the x-axis at the equilibrium position of the moving end of the spring. And again, I'm going to attach a mass to the moving end of the spring and pull out the mass, so the mass is now at x equals a. Now what we're going to do is at time t equals 0, I'm going to release the mass from rest, and the mass is going to begin to oscillate back and forth. What I would like to be able to do now is to predict the position of the mass at any time I'd like. If I am releasing the mass from x equals a at time equals 0, I would now like to know where will the mass be at time equals 1 second, where will the mass be at time 2 seconds, where will the mass be at time 3 seconds, and so forth. In other words, what I would like to do is to be able to express the position of the mass as a function of time. In other words, what I'm looking for here is a function x of t, which will tell me where is the mass at any particular time. We're going to solve that problem using a trick. We're going to compare the motion of the mass circling at constant angular velocity with the motion of the mass here going up and down at the end of a spring. Notice that if the angular velocity of the circling mass is just right, then the vertical coordinate of the circling mass exactly matches the motion of the mass on the spring. Notice that this only works when the angular velocity of the circling mass is just right. If that circling mass had an angular velocity that was too fast, or if that circling mass had an angular velocity that was too slow, then the motion of the circling mass and the motion of the mass on the spring would not match up. What we want to know is, for a specified mass oscillating at the end of a specified spring, what exactly does the angular velocity of the circling mass need to be so that the motion of the circling mass and the motion of the mass on the spring exactly match? In this figure, I've tried to simplify things by having the mass on the spring go back and forth horizontally instead of vertically, as we did in the demo. I have the circling mass moving on a circle of radius a, and I have aligned the center of the circle with the resting position of the spring. The circling mass always moves at a constant speed. That speed is given by a formula which we encountered earlier on in our study of rotational kinematics. Remember that the speed of an object moving in a circle is equal to the radius of the circle, which here is a, multiplied by the angular velocity. So the circling mass is always moving at a speed equal to a times omega. Now, look at the motion of the circling mass and the motion of the mass on the spring together. There are only two moments in each cycle where the velocities of those two things are exactly the same. The two moments in each cycle where the velocities are exactly the same are those two moments where the mass on the spring is going through x equals 0. So if we look at that cycle, then we have one moment right here where the mass on the spring is going through its resting position going to the left, where the velocity of the mass on the spring and the velocity of the mass making the circle exactly match. And then we have another moment later on where the mass on the spring is going through its resting position rightward. At that moment right there, the velocity of the mass on the spring and the velocity of the mass making the circle exactly match. So in this figure here, I have concentrated on one of those moments where the velocities match. The mass going around the circle always has a speed of a omega, and at this moment, the mass on the spring has its maximum velocity, which we reviewed earlier in the video. We see then that the speed of the circling mass and the speed of the mass on the spring match only at the moment where that mass on the spring takes on the maximum value of its speed. In other words, the speed of that circling mass, which is always the same, must be equal to that maximum speed taken on by the mass at the end of the spring. The speed of the circling mass is a omega, and that maximum speed taken on by the mass on the spring is equal to a times the square root of k over m. We see then that the angular velocity, which the circling mass must take on in order to match the motion of the mass on the spring, is equal to the square root of the spring constant over the mass. In the next video, we will use this result to actually express the position of the mass on the spring as a function of time.
Thank you for watching.